So I'm really excited to be here. Like Bill Venner's, my laptop has a bit of a slant on the front, so I have to stand here and hold it to make sure it doesn't fall off this stand. But I'm going to be speaking about the project formerly known as Scalaz Stream today, now known as Functional Streams for Scala, or FS2 for short. So I'm really excited to be here, and I'm excited because this is over. We did a bunch of redesign work in Scalaz Stream, and specifically there was some really nasty resource allocation problems in light of like asynchronous operations, where sort of our killer feature, if you will, of making sure resources are cleaned up no matter what type of thing occurs was failing in various cases, right? And if it's like our big killer feature and we can't deliver on it, it's pretty embarrassing. So in the summer of 2015, Paul Chiasanu started what we thought would be a mild redesign work. We were thinking maybe a month or two worth of additions to the core algebra of Scalaz Stream. And where we ended up about 15 months later in September was a brand new library. And it really is a brand new library. I don't think there's a line of code that's shared between the two systems. So for today's talk, I sort of had the option of either doing a brief introduction to the library and sort of getting you started, or sort of showing all of the fancy things we can do with it, or doing both. But fortunately for you, Alexi only gave me 40 minutes, so we're going to do the intro. Before we get started, I do want to kind of contrast, though, 0.8 and 0.9. So series 0.8, it's in the Git repo here. It is actively maintained. We just recently published 0.86. We published it for Scala 2.10, 11, and 12. It's currently published for Scala Z 7.1 and 7.2, and we will publish a version for 7.3 as soon as that's out of milestones or release candidates. We do have some dependencies there, certainly, right? The library does depend on Scala Z, hence its name, and it has a dependency on scodec bits for some binary manipulation. And it is actively maintained, and we do that because we know the jump from Scalaz Stream to FS2 is big, right? Everybody has the appropriate time in their own business when it makes sense to take the time out to do this transition. So we are actively maintaining this. We're open to adding some features, but if you want to add like something huge, talk to me. But Series 0.9 is what we released a few months ago. And it's quite a bit different because the FP landscape in Scala has changed quite a bit in the last 2 years. We do have no dependencies, right? So you can sort of guess, like anytime someone says they have no dependencies, it really means they're reinventing everything themselves. We did that. We do have support for Scala.js, so you can do like full FP, resource-based streaming in the browser. And we have bindings for lots of different, libraries in the community. We do have Scalaz and Cats bindings, and we also have bindings to a bunch of other things I'll talk about in a bit. Most importantly, our library is correct, right? The whole goal of the 0.8 to 0.9 transition was really making sure resource allocation was bulletproof, that there was no type of strange edge case where if you did something, in a very specific set of interleavings of processor execution, we'd miss some resource allocation free. So we did that by defining this very small core interpreter. And when you look at like the Stream API that I'm going to show today, we're just looking at the surface API around a small core interpreter. To give you an idea, the internal Stream core interpreter that's in the guts of FS2 is 9 primitive operations. And everything else in the library is built from those 9 primitive operations and in a very combinatorial explosion type way, right? So the primary type in the library is this stream type. For folks familiar with Scalaz Stream, this is analogous to process. And it's parameterized by 2 type parameters, right? We have this F type, and we have an output type O. And so when we think of a stream, we think about getting values out of it, right? Pulling values from it, and that's our type O there. Our type F is some type of effect that we're going to evaluate potentially while pulling elements from this stream. And we might evaluate that effect for various reasons, right? We might evaluate effect because we want to generate an O value. But we might also evaluate an effect just for the purposes of the effect, right? So a really good example of this, I think, is that like if we want to open a socket to a server, right, we're going to evaluate some effect that opens a socket. And there's no output to that, necessarily. Or if we're going to close a socket or open a file or close a file, all these effects we're evaluating for the purpose of what they're doing to the outside world, right? But then other effects, like reading bytes from a file or reading bytes from a socket, is going to produce some output value, and that's our output of type O. So let's look at constructing a stream via the stream apply, the stream companion apply. So here we have this val s, and we've created a stream with 3 elements, a discrete stream. And I think what's interesting about this example is that the effect type here is set to nothing, right? So anytime we set that effect type to nothing, what we're saying is we have a stream that cannot evaluate effects, okay? Now later we could come in and say, well, but I do want to read from a file, or I do want to write to a file, and we can sort of fix that up. But we use this nothing type to indicate that this particular stream is not going to evaluate any effects. And as you can imagine, the stream API provides this sort of collection-like API. We can map, we can append, right? We can do all sorts of things. And in this particular case, we can call this toList method. And so if our stream has no effects, right? If we have that nothing type for our effect type, then we can convert our stream to a strict collection, right? And kind of go back to the collection API. We also have other sort of collection-like APIs that don't exist in the standards collection library. Intersperse is one of my favorites because it's super useful, right? But like stick a 0 between elements, right? And again, we can call it toList because we have a pure stream. And that's sort of the way I want you to think about this notion of having like a nothing for an effect type, is that it's a stream that's pure, right? Because we have no effect evaluation occurring. This is the to-do MVC app of streaming libraries, or the FizzBuzz of streaming libraries, right? The Fibonacci sequence. And the reason we use the Fibonacci sequence is because it does show a certain number of properties about a streaming library. Here we have this fib stream. It's a pure stream. You can see the effect type is nothing. We start with a stream of 2 elements, 0 and 1. And then we append to that fib zipped with its tail. Right? And we combine the 2 elements, like the elements from fib and the elements from fib's tail, using just integer addition. And that's infinite, of course, right? So we've got some interesting properties we can sort of guess here. There's some infinite behavior going on. There's something that's handling like making sure we don't overflow the stack. And then we can take the first 10 elements and again convert back to a list, and we have the Fibonacci sequence. Unlike the built-in stream type in the Scala standard collections, we do not do any memoization. So like this will be snappy, even on this old MacBook Air. If you said take 20 elements, go get coffee, right? So this is not necessarily the best way to define a Fibonacci calculation, but nonetheless, it does show some interesting properties of streams. How many people have used task? OK, about half. So I want to look at effectful streams. And in order to talk about effectful streams, we have to talk about what it means to evaluate an effect. So here I have this task of sample. The idea here is that the val sample describes a program that when we evaluate it, it's going to go off and like read some hardware sensor. Right? And maybe it reads like the amount of heap that's being used by the JVM, or reads something off of a PCI bus or something. So every time this sample is evaluated, we're going to call this sensor.read method and return the result. Okay? And we can stick that into a stream using this eval constructor. Right? We can call stream.eval. And what that will yield us is a stream of task comma sample. Right? So we've sort of like taken apart the task sample and sort of moved those 2 types into position into the stream type constructor. Now, if we just say stream.eval sample, we get a singleton stream, a stream of 1 element. And so we repeat it, right? And repeat will just infinitely, continuously generate values. And then we might want to do something with this. So let's say in this particular example, we take the first 10 elements from the stream. And by taking 10, we've taken this infinite stream and turned it into a finite stream, right? One that, as someone pulls from it, once they've pulled up to 10 individual elements, then halt, even though the source was infinite. And then in this case, we use this run log method, which is sort of like a sink, or sort of like a terminating point, where it's going to pull elements into a vector, right? And it's going to keep pulling until we reach the natural end of the stream. So what we get back in this particular case is like a task of vector of sample. Since we're still in our task constructor, all we really have done is sort of taken a streamy description of the program we wanted to build and turned it into an effectful description of the program. Right? So nothing has occurred at this point. It's sort of like a compilation step. Right? And then finally, somewhere towards like the end of the universe, we can call this unsafe run method to say, like, now I want to go do my effects. Right? And in FS2, all throughout, anywhere you see a method that starts with unsafe, you should close your eyes. In general, these are the places where things happen. Right? Nothing else happens until then. And don't worry about the code on this slide, but there are a bunch of different ways to run effectful streams. Is sort of the point here. We've got like four ways built into the library, and if you use some of the interop libraries, there's some additional ways. They all start with run, and they all require something about our type constructor, something about our f, or our effect. And specifically, they require this instance of this catchable type class, which I'll talk about more in a minute. But because of this, if we had a pure stream, we can't call like run log, because there's no catchable instance from nothing. Right? So you can sort of think of like pure streams and effectful streams. With pure streams, I can always call toList, toVector. And on effectful streams, I have these run methods. OK, so once we have streams, the next sort of most normal thing we want to do is transform the elements of streams. And we do that with pipes. OK, so pipes are kind of interesting in that we have input values of type I. We have output values of type O. And we can also evaluate effects while we're transforming things. OK, so it's a little bit different than maybe for folks that are familiar with a Scalaz stream with process 1, we weren't able to evaluate effects. We had a different type to do that. But here we have this ability to evaluate effects. And this is maybe an example of what stream evaluation might, or stream transformation might look like. We have two pipes defined here, UTF-8 decode and lines. The UTF-8 decode pipe is going to pull bytes in, right, from some source stream and turn them into strings using some UTF-8 library. And lines is going to pull strings in and output strings, but maybe like re-chunk the strings based off of carriage returns, right? And then, in this example down below, we can do something like read all of the bytes from a file in like 4K chunks, and then use this through combinator to say, take the output of that original source, put it through the UTF-8 decoder, and then put it through the text.lines, reparser. And so this is the way we will go about doing stream transformations throughout the library. We can also combine streams, right? Not just transfer them, but combine them. So here we have Pipe2, which says I want to have two different inputs. I've got a stream that has some output of type I and another stream that has an output of I2. And I want to hook those both together and create a new stream that outputs something type O. And again, I can evaluate effects when I do this, right? Maybe look at the values and go off and read a socket or something. Okay? And we've seen an example of Pipe2s already because we saw this zip width thing. Right? Here we had two streams. We had fibs, and we had fibs' tail. Those are two distinct input streams. And we combined them via this addition method. Now, this is pretty syntax on top of something that's pretty terrible. We do have this through-to combinator. Through-to is like the Pipe2 equivalent of through. And maybe it's not so bad. You can see there's like this zip width Pipe2 on the far right. So there's some object called Pipe2 that gives us instances of the Pipe2 type, right? Then get this like funky pure thing, which is to avoid some inference things. So don't worry too much about it. We provide nice syntax for all of this, but we have seen this example of combining streams already. And there's a bunch of different ways to do this. So like in this particular case, we're using pure streams. X and Y are both discrete pure streams, and we just interleave the elements. And again, that's dressing on top of this uglier through-to application. Okay. So besides transforming and combining, we also might want to sync streams, put the values somewhere, go do something with them. And we have this sync type. So again, we have like an input type I, but we don't have any outputs, right? And we can evaluate effects of type F. So a good example of a sync might be writing to a file, right? In this particular case, we're using like the IO package from FS2, and we create a sync that writes all bytes that are sent to it into my file, inside of the task constructor, okay? Inside of the task type constructor. And we can apply syncs to streams via the to combinator. So here we have like some stream of lines, some stream of task comma string, and we just send the output of that to our output file. And of course, nothing has actually occurred yet. We've built up this streamy description of what's going to occur. And we sort of compile that or reinterpret that into an effectful description of what's going to occur. And then eventually, at some point, run that program. We saw Jay talk about Kafka, last talk. We do Kafka, you can do Kafka stuff with sync. So you can imagine like consumers from a Kafka topic as streams. And you can imagine writing maybe events to Kafka, using syncs, right? Write all the events to a Kafka topic with a sync. And this is sort of kind of taken from some of our code at work. We basically go and create some sync that represents a specific data type being written to Kafka. And maybe we like map some elements and then eventually sync this source stream into a Kafka topic. Again, running it at the end of the world. So this is sort of my favorite part of FS2. So how do we compose these things together? We have pipes, we've got syncs, we've got Pipe2s, we've got streams. We've heard a lot this week that like the ultimate way to evaluate a library is to see how well it composes, right? So here's something I really like about FS2. A pipe is really just a type alias for a function 1. Okay? So this is really meaningful. This is an interesting thing about the library. A pipe FIO, we have an input of stream FI, and it returns an output of stream FO. So for anyone familiar with Scalaz stream and the way process 1s were defined, it was very much different, right? Process 1s were like sort of a special type of machine that could sort of kind of like pull elements from places. And it was really confusing, and I think like 3 people in the world understood it. Function 1s, everybody sort of gets, right? And similarly, pipe 2s are just function 2s. And syncs are just pipes whose output type is set to unit. Okay? So this means it's really easy to create your own pipes, your own syncs, and your own pipe 2s, right? Because these are just functions. And of course, we can do like fancy function composition with existing operators. Here we're just saying text UTF-8 to code and then go to lines, right? It's just function composition. And so a lot of times you'll see like people come to the library and say like, oh, I'm really stuck. I want to figure out how to put this thing into that thing. And they forget that like a pipe is really just this function 1 alias. And as soon as they remember that, like, oh, no, I know how to do this, right? It's a really sort of important point in FS2 composition. How many people have done the README example in FS2's Git repo? OK, so some. So good. I was afraid like everyone would raise their hands and we'd have to skip this. But when Paul Chiasano first sort of announced Scalaz stream at like any Scala in 2012 maybe, he did this example. And this example now has been ported to FS2, and I want to take a look at what it looks like. The general idea is that we've got some file on disk called Fahrenheit.txt, and we want to read it in and convert it to a new file on disk called Celsius.txt. And like all big data shops, this is going to be a 10 gigabyte file on disk, and we need to do all of these conversions very quickly in constant heap. So bear with me. So the way we do that here is we use, again, this I/O package from FS2, and we say, read all of the bytes from this Fahrenheit.txt file in 4 kilobyte chunks inside the effect task. We then want to push those bytes through that pipe we just composed. Right? So we take this UTF-8 decode, do the line chunkiness. And then we want to start using some collection-like operation. So here we get rid of like all empty lines. We get rid of all lines that start with comments. We map over each individual line and parse the string as a double, convert the double from Fahrenheit to Celsius, then convert it back to a string. And you might think like, whoa, that what if the line's like ASDF? It's going to blow up. It'll throw an exception, and that's fine. Like we catch that exception, we handle it appropriately inside the stream algebra, right? So you don't necessarily have to switch to returning like ethers or tries or something. We do handle exceptions thrown from pure functions in the library. Now that we've had like this stream of Celsius values, we want to stick new lines back in between all of the strings, re-encode it to UTF-8, write it to some file on disk, and then run that overall program. And now what we've got back is this converter value whose output type is meaningless, right? It's a task that says when we go and evaluate this, we're going to do this conversion in constant memory. We're going to be pulling elements as fast as we can write them to disk. right? So you can have a 10 gig file, and this all works fine. But it doesn't have an output value, right? We have a task of unit, which is the result of calling this run at the end, which is to say that this program, this effectful value that we've evaluated here, exists solely for the purpose of doing this stream transformation on disk. We don't care about the output value. And at some point, we go off and we run that, and we actually go to disk and do our I/O. Okay? Does that sort of make sense? All right. So we had resources being allocated there. We had input resource, like a file handle we were reading from. We had a file handle we were writing to. And we do this via this bracket method. So don't worry too much about the signature there. But the general idea is that we're going to have some effectful value that tells us how to go get a resource, like go get a file handle or go open a socket. And then once we've done that, once we've successfully opened a socket or gotten a file, we want to generate some stream from it, like pulling bytes from it. And then we'll also give it some callback to tell it how to close that thing at the appropriate time. And what we're going to do is sort of decorate the stream that comes back with resource allocation and management logic, such that if the stream ends in any way, we're guaranteed that our release action will be called at the appropriate time. And the release action sort of needs to be called at the most opportunistic time, right? You can't just say, well, when the JVM exits, we'll sort of build up all of these individual release calls and eventually get around to calling them. We want to sort of get to it as soon as we can, right? Even in light of streams that go off and evaluate things asynchronously. And this starts to get to the core issue that FS2 addresses. So it's worth pointing out that there's multiple ways a stream can terminate, and there's basically 3. We can reach the end, right? We've seen a lot of finite streams, like stream 1, 2, 3. And so when we pull the last element out of stream 1, 2, 3, we've reached the natural end. But we also saw infinite streams where we did take 10, right? And in those types of streams, we have this early termination that occurs, where some combinator, some pipe decides to stop reading, don't pull any more elements. And then finally, we have errors that occur we might want to terminate overall execution from. And so even in light of all of those different types of errors, we need some way that this resource allocation can occur. And the way we do that is with this pull data type. So the general idea is that a stream can be opened. So a stream FA for any FA can be opened, and we get a pull of FAR. And pull's going to let us evaluate effects. It's going to let us output values of type A. And then it sort of lets us pass around this value of type R, this resource of type R. Pull can also acquire resources, like going out and getting a file handle or going out and opening a socket. And so when we open a stream, we're in this pull effect now, and pull forms this monad in our R type. And so what we can do is decide whether we want to pull elements from the source stream that we opened, or maybe just want to output things anyway. Maybe we want to output 2 of everything we get. But eventually, we decide what type of things we're going to do with the source stream, and then we close it, and we get back to a stream again. Maybe a modified stream, a stream that looks like some transformation on the original. Yeah, Joe?
So the type is pull far. How far does it pull?
Very far. I didn't notice that. That's good. That's good. So more specifically, when we open a stream, our R type, our resource type, is a handle. Okay? And a handle is literally a handle for the source stream that we can pull elements from. This is a really important point. You might have noticed it as I've been speaking. FS2 is completely pull-based, right? There's no pushing that occurs. And as a result of that, back pressure is just natural. It's baked in, right? Or maybe back pressure is even a type error to apply to this system, because it makes no sense to talk about back pressure in something that pulls. Now, we do have ways, if you want to do push type mechanisms, there are ways to do that with FS2 in a back pressure-y sort of way. But the general notion here is that we get these handles, and these handles let us pull elements from the source stream. And you can see the handle is sort of sitting in that monadic point of our pull data type. Right? So here's a way we might use this pull handle structure to implement head. Right? So this is a combinator that would just get the first element from a stream and terminate. And the idea is that we would take some source stream and open it, and then we would call flat map on it. So now we're inside of the pull effect. And what we get is our R type. We get this handle, H. And with this handle H, we'll say pull 1 element, receive 1 element from the upstream, from our source. Okay? That gives us a tuple. It gives us the single element that we asked for, O. And it gives us like a continuation, sort of, a new handle if we want to read more elements. And we don't care about that here because we just want to output the first. So we use this output 1 constructor to say output the 1 O we got, and then close the overall stream. And what we end up with is a non-blocking implementation of the head combinator that works for all types of streams, regardless of where they're coming from, regardless of what type of asynchronous behavior that exists in that stream, which guarantees resource safety. Okay? So sort of like a little DSL, if you will. You can imagine some nice free algebra sitting underneath this, which is exactly what does sit underneath of this. Similarly, we can implement tail, and it's like the same exact pattern, but we ignore the first O value, and we take that next H, and we just echo it. Right? So the h.echo is sort of this built-in convenience operator that just says, start pulling elements and outputting everything we get. Right? So we throw away the first value and echo. So has anybody defined like custom graph stages for Akka streams? Right? This is sort of what we're doing here, the equivalent of like a custom graph stage. So it's all type checked, and you get very nice compiler errors if you get it wrong. And this pattern of like go and open a stream, get into the pull effect, run some function that reads a handle, right, and returns a pull, and then close again is so common that we have this source.pull alias for it. So think about the type of f in source.pull, right? F is a function from handle to pull, right? Because we're going to do something with a handle and return a new pull that has either outputted elements or decides how we're going to terminate the stream, something to that effect. And so what you can start building up are nice recursive pulls. We can say things like take. This is a reasonable definition of take in FS2. And we'll define it recursively. We'll say take works for any effect f and any type a, completely unconstrained. Right? We know it's unconstrained because we've provided no constraints on these types. Right? And we're going to return this pipe FAA. And at the very bottom of our body of our method, we're going to just materialize some source, right? Because remember, a pipe's just a function 1. So we're going to materialize this source stream source, and we're going to pull something from it. And we're going to replace these question marks with some function from handle to pull. And so we'll define this loop as a recursive function. Right? So loop will have state, like the number of elements remaining. And what it's going to return is this function from handle to pull. Okay? And then inside the function, we can just say if remaining is less than or equal to 0, we're done. Stop pulling, close the overall stream. And otherwise, receive a single element from our source. We get like that single element A, and we get a new handle, which we shadow our old handle, output the A, and then go and loop again. Right? So you can imagine there's some type of stack safety here that's occurring to make sure all of these binds, all these flat map calls end up getting trampolined. And that greater than is just the and then operator. It's like flat map that ignores its input value. Right? And we can sort of do this in all sorts of interesting ways. Right? The same basic pattern of writing recursive pulls scales really, really, really well. So here we have this method that exists in a system of mine called buffer async. And the general idea is we want to like pull things as fast as we can and stick them in a bounded queue. And then have those elements sitting in the queue so someone else can pull from that queue as fast as they can. And that provides us a certain amount of parallelism or a certain amount of concurrency in the stream processing so that as systems are off processing, we're pulling more data. And so we can define this again recursively. In this case, we end up using the bounded queue constructor from the async package in FS2. And we go and allocate this queue. Now the return type here is challenging. We get this f of q of f attempt option chunk A. The important part here is we've allocated a queue inside of this f type constructor. So you can sort of think of the return from bounded queue as being like a factory that builds a queue. That when we go and evaluate make queue, that has the effect of generating this queue in memory somewhere. And as long as you then use that same queue for all NQ and DQ operations, we're safe. If you were to evaluate this 2, 3, 4 times, you end up getting 2, 3, and 4 queues created on heap. Right? And then with this queue, we can do things like let's evaluate it, get it into the stream algebra, And then flat map that singleton stream that comes back from that, and now we have access to the real allocated queue, okay? And then with that real allocated queue, we sort of want to do two things. We want to say, start pulling from the input and writing the values into the queue. And so we chain together a bunch of combinators here. We say start with some source stream, get access to the underlying chunks. So inside of FS2, all of the individual data elements are actually put in like a collection called chunk. It's sort of like vector, but it's faster in various ways, right? For our use cases. It can do things like non-boxed, byte arrays, things like that. So it'll be fast. So sort of like let us access these internal chunks. We have this none terminate thing, which wraps every element in a sum until you hit the end of the stream, in which case it gives you a single none. We have this attempt thing that tells us about errors that occur, and then we write it all to a queue. And then we drain the queue. We say we're going to write the things to the queue, but we don't care about like any output of that. The whole point of doing this is just getting them into a queue. And so what we end up with is the stream that has no output, right? Its output type is nothing. And then we have another stream we want to create to read from this queue. And this is the one we want to return to people, right? So we read from the queue. We say queue.dequeue, and then we sort of undo each of the combinators we stack together, right? We say like rethrow any errors that might have occurred, and that sort of gets rid of the attempt thing out of our type. Unnone terminate, like take all the sums and turn them back into values, but as soon as you hit a none, we're at the end, right? And then kind of undo the chunkiness, like take those chunks and stick them back, emit them as individual chunks into the stream. And so what we get back is this stream of FA. And now how do we sort of run these two things and like race them against each other? Right? We want to have someone filling and someone pulling. And we use this async operation called merge. And in order to use merge, in order to do the make queue, we need to define something on F. We need to constrain F in some way. And so we had this async type class we use, some type class that describes the ability for a type constructor to do things asynchronously. So I said we have no dependencies, which means we reinvent things. And we reinvent them badly, because we don't want to provide a third alternative to the functional type classes, right? We've defined a very thin set of type classes, very minimal number of methods, minimal syntax, just the things we need to get the library built and to start defining custom pipes and other combinators. And so here we have functor, applicative monad, and traverse. Like we don't have a fancy laws framework. We don't have all of the other types of functors, right? And we have no plans to, right? We do not want to be another functional library. But we do need a set of data types, a set of extension type classes to do the things we're talking about, to remain polymorphic. And so we have this catchable type class. You can sort of think of catchable as a monad that lets us catch exceptions that occur during evaluation. We have a suspendable type class, which is sort of like monad suspend from, I think PureScript has it. That lets us talk about like delaying, right? Like lets us talk about like deferring evaluation of something. We have an effect type class, which is a catchable suspendable that lets us evaluate things asynchronously. It's kind of weird. And then finally, we have this async type class, which is an effect that lets us create memory cells. And this is kind of cool. The idea here is that the primary operation on async is the notion of going and creating a ref. And if you create a ref, it's like a cell in memory that supports it supports basically compare and set. And for folks that know distributed systems, you can build all concurrency primitives with compare and set. So we did. We have our own semaphore. We have our own queue, which we saw already. We have our own signal. We have an entire non-blocking concurrency library, like all internally callback-based, right, based off of some execution context or thread pool, but built up on top of this notion of an effectful ref, an async ref, which is very powerful. OK, so why do we care about all of these type classes, right? And we've seen this in a lot of talks this week. We care about it because it lets us reason about what's happening. We can look at a particular combinator and get a pretty good clue right away as to what's going to occur inside of the definition of that combinator. When we looked at UTF-8 decode earlier, we saw that the effect type was unconstrained. So we knew it couldn't have any effects. right? It couldn't be going out and reading the network or allocating memory cells or evaluating effects asynchronously because we knew nothing about that effect type F. And so that's very powerful. But admittedly, it's maybe a little unsatisfactory when you first come to the library, right? You just see all these F-type constructors everywhere, and it's a bit overwhelming. So maybe a more practical benefit of this is that there are lots of task types. FS2 has a task type. There's the Scalaz effect task type. Monix has a task type. And there are plenty of other type constructors folks use. Like Dustin right now is using the F as free, as cats free applied to a specific algebra, right? And like in my business, we have this type called trace task, where we effectively do like Zipkin-like tracing of task evaluation and write all of the spans that occur out to some storage system. And so we want to be able to run streams in that effect type. All right, so in the last 3 minutes, I want to look at a system that we built at Comcast. It's basically a network analysis tool. So think sort of like Wireshark or Ethereal, like that type of system, but run in like a lights out type of mode. So we have all sorts of different capture sources where we pull stuff off the network, and we maybe optionally record the data we're seeing. We do some domain-specific decoding of the data we're seeing, and then a whole bunch of rules analysis on different patterns in the data, and then write it to a bunch of different outputs. And we represented this entire system as a stream and a set of pipes. Okay? And so this particular application, as you configure each monitor, each thing that we'd go and look at, effectively what we would do is build up this big stream pipeline. We'd start with this input type that read some timestamped values from a capture source, and then hooked it up to a bunch of pipes that were defined based off of the data types in the system. This is like video type stuff, right? So if it's like a MPEG video stream we're looking at, maybe the source is going to pull from a coax device, and maybe we're doing some type of MPEG decoding and MPEG rules analysis on the values. And what I want to focus on right now is the capture source, because there were a bunch of different capture sources we supported. The first was UDP datagrams, right? Like if someone wanted to run the application and they had their own system, they wanted to have that system send messages directly to our monitor and let it do its analysis. And we could do that because FS2's got this UDP package built in, built on top of Java Nio. But you can see it provides this very high-level streamy DSL for working with UDP. Here we're saying in the task constructor, bind to some address. We get back a socket if we flat map, and then on that socket we can read datagrams out and emit them into our system. We did libpcap-based monitoring, right? So we took libpcap and put a native wrapper around it, and now we've got some resource we need to manage because we got to go to the operating system, to the kernel, and say let us start monitoring the NIC card for packets. And then once we start monitoring that NIC card, we have a kernel call to pull data from the kernel, pull elements from the kernel. We did RF device type stuff, which again is sort of a combination of the previous two. We've got some UPnP discovery process where when you open a connection to some coax device, some set-top-like device on the network, we can go configure it and go talk to it and get it to start streaming data to us, but then we want to start receiving UDP. And so we can sort of put together the bracket combinator with maybe some of the UDP combinators to do that in a nice way. And then we did this PCAP playback, where we have a recorded file from TCP dump. We want to play it back at maybe different clock speeds. I won't have time to go through it in detail, but PCAP playback is really interesting because you want to play it back at different speeds, and we have this state machine to do it. And I am out of time, so I won't show the details, but the cool thing is you can represent state machines in FS2 as co-recursive functions using the same exact pull, recursive pull structure we saw already. And you just gradually build up these state machines and implement every state as a co-recursive function inside of a big pull. So that's all I have. I am out of time, so I won't have time for questions, but if anyone wants to talk FS2, come find me later today. Thanks, Zach.